Welcome back to the deep dive. We are doing something a little dangerous today.
Dangerous. I thought we were just writing code.
We are writing code, but we aren't just writing any code. We are, venturing into the territory that makes grown developers cry.
Ah.
We are going into the land of floating point arithmetic.
Ah, yes. Okay. The land where 0.1 plus 0.2 does not equal 0.3.
Exactly. And, usually on this show, we take a stack of articles, we read them, and we talk about the concepts. But today, we are trying a different format, a coding session.
Right. We're going to build a library from scratch based on the source material provided, which is this really fascinating Rust library called Titan Arithmetic. We're going to try and implement it line by line right now.
So I want you, the listener, to visualize this. I have a blank text editor open, dark mode, obviously.
Of course.
The cursor is just blinking there on line 1.
Yeah.
And we have a mission.
The mission is robustness. We are building a toolkit to handle sort of the sharp edges of math. Because as you alluded to, computers are actually, they're quite bad at math.
Or at least they're bad at real precise. But, history is just littered with disasters caused by floating point errors.
Oh, absolutely. The classic example, the one everyone brings up, is the Patriot Missile failure in 1991.
That was a floating point error. I didn't know that.
It was. The system's internal clock measured time in tenths of a second, but it stored that value in a 24-bit fixed register.
Okay.
Now, the number 1/10 in binary is an infinite repeating fraction, like 1/3 in decimal.
So you have to chop it off, son.
You have to chop it off. And that tiny chopping error, the precision loss, it was minuscule. Too small to notice at first, but the system had been running for 100 hours.
And the errors stacked up.
They compounded.
Full defense.
It's a lifetime. An incoming Scud missile travels over half a kilometer in that time.
So the missile just missed.
It missed. It hit a barracks instead. 28 people died, all because of a rounding error.
Wow. That puts a heavy weight on our blinking cursor today. We aren't just typing code. We're, trying to prove...
Tame implies strength, stability.
It does. We're going to write 5 specific utilities that solve the most common, just headache-inducing problems in floating point math.
Yeah.
So that's precision, equality, sorting, animation, and type safety.
And we're doing this in Rust.
Which is my favorite language,
Yeah.
but it's also famously strict. It doesn't let you get away with sloppy math easily.
That's why it's perfect for this. It forces you to confront these problems head on. So are you ready to start typing?
I'm ready. Line 1.
Yeah.
Okay, if we're doing arithmetic, we need to be able to add, subtract, that kind of thing. So, standard library imports.
Yes. In Rust, you can't just assume your types will act like numbers in a generic context unless you explicitly tell the compiler. So we need to import the operation traits.
Okay, I'm typing this out now. Use std.ops.
That's
Add sub mul div.
add sub mo div.
It sounds like a strange chant.
It really does.
Yeah.
Now, to be clear, since we are mostly going to use the concrete F32 type, the 32-bit float, we don't strictly need these for the basic math.
Right, the built-in floats already know how to do this.
But if we ever wanted to make this library generic later on, so it could work with F64 or some custom number type, these traits would be essential.
It's good practice. It sets the stage. It tells anyone reading the code, we are building mathematical operators here.
Okay, imports are done. Easy part over.
And now we face the first boss battle.
The source document lists a function called difference of products. This is a deceptively simple-looking problem.
The mathematical goal is just to calculate A times B, C times DD.
Right, so if you were just writing this in a hurry, what would you type? No thinking, just type.
I'd probably just write A, B, C, D. Done. Ship it.
And for 90% of the numbers you throw at it, that would be fine. But for the other 10%, you have just introduced a bug called Catastrophic Cancellation.
Catastrophic Cancellation. That sounds like a heavy metal band name.
It's worse. It's a numerical analysis nightmare. Here's the scenario. Imagine A times B bore results in a very large number. Let's say 1,000,000.5.
Okay, 1,000,000.5.
And imagine A times D door results in 1,000,000.4.
So they're huge numbers, but they're very, very close together.
Exactly. The true difference is 0.1. But remember, floating point numbers have a limited number of significant digits. They can only hold so much information.
Right, like a fixed number of slots for digits.
Pretty much. And when you have a number as big as 1,000,000, the computer might not have enough room in those slots to store that 0.5 or 0.4 with perfect precision. It might have to round them.
So 1,000,000.5 might get stored as just.
1,000,000.
Or 1,000,000, depending on the rounding mode. Now you do the subtraction on these rounded numbers, you get 0 or maybe 1, but the real answer was 0.1.
You've lost all the important information.
You haven't just lost a little precision, you've lost all of the significant information. The cancellation of the big numbers in front left you with nothing but garbage, just noise.
So we need a way to do this calculation that preserves those tiny details, even when the numbers themselves are huge.
Exactly. We need a variation of an algorithm that uses a special hardware instruction.
Okay, let's define the function signature before we get into the guts of it. I'm typing #inline, always.
Good call.
Why are we being so aggressive with the inlining here? Usually I just write #inline and let the compiler decide.
Think about what this function does. It's a couple of multiplications and a couple of additions. It's tiny.
If the computer has to perform a full function call jump to a new memory address, push all the variables onto the stack, run the code, pop them off, jump back, that administrative overhead might literally take longer than the math itself.
So #inline, always, is us grabbing the compiler by the lapels and saying, do not make this a function call, just copy and paste the machine code right here where I'm calling it.
Precisely. We want the safety and readability of a function, but with the raw speed of just writing the operations directly.
Okay, makes sense. So the signature, pub fn difference of products, AF32, BF32, CF32, DF32, minus F32. Standard stuff. 4 floats in, 1 float out. Now, the body,
This is where I get to be clever. Step 1. Calculate the second product.
let CD is CD. Easy enough.
Okay, this is a standard multiplication. It might have small rounding error, but we're going to store that potentially flawed result.
Okay, now step 2. This is where the source code gets really interesting. I'm typing let air-c dot mulad beerlad. I've seen this in the Rust docs, but I have to admit I've never actually used it. It's f32.mulad.
This function is special. It corresponds directly to a hardware instruction on most modern CPUs called fused multiply-add, or FMA.
Okay, explain FMA to me. Like, how is it different from just doing a multiply and then an add?
Okay. Normally, if you tell a computer to calculate xy plus z, it does it in 2 distinct steps. First, it calculates xy. It takes that result, which might have, say, 50 digits of precision.
And it has to cram it into a 32-bit float.
Exactly. It rounds it to fit into the available space and puts it in a register. Then it takes that already rounded number and adds z to it. And what does it do after the addition?
It rounds it again.
It rounds again. You have 2 rounding steps, 2 chances to lose data.
Okay, I see where this is going.
Fused multiply-add is a special dedicated circuit in the CPU. It takes x, y, and z all at once. It does the multiplication and the addition in a single atomic operation, using a much higher internal precision, like 80 bits, and it only rounds the final result once at the very end.
It's fundamentally more precise.
Much more precise. So, look at that line again, -ec.mulad-d.
We're calculating NEC times D plus CD day.
Mathematically, what is CD times plus CDD?
It should be 0.
It should be 0. But remember, the variable CD, the one we calculated in the first line, was done with a normal, imprecise multiplication. It has a rounding error baked in.
But the mule calculation is done with the high precision FMA.
Yes. So what you're doing is subtracting the low precision version from the high precision version. The result of this line, which we've cleverly named error, is literally the rounding error of the product $d times dd. We have isolated the mistake the computer made.
That is genius. We're not just doing math. We are literally auditing the computer's math as we go.
Exactly. Now line 3.
Okay. Let D a.mulo b -cd.
Dop for difference of products. Here we use FMA again. We calculate A times B plus MIDI CD. This gives us the main part of our answer, again with that high FMA precision.
But wait, D is still using that CD variable, which we know has an error in it, so D is still slightly wrong.
You're right, it's close, but it's biased by that first rounding error, but we have that error, don't we?
We have it in the error variable. I see the final line. Dop plus error.
We just add the error term back in.
Yeah.
If the computer rounded CDD down by 0.00001 in the first step, then error will hold positive 0.00001. We add it back, restoring the precision that was lost.
This is incredibly elegant. 4 lines of code, but it essentially emulates a much higher precision calculation using only 32-bit operations, just by being smart about tracking where the errors live.
It's a technique called error compensation, and if you're building a physics engine or a financial modeling tool or anything that runs for a long time, this single function is the difference between a simulation that stays stable for days and one that just explodes in 10 minutes.
Yeah. A quick question. We didn't have to check for hardware support for FMA. Does Rust handle that? What if I'm running this on, I don't know, a Raspberry Pi or some customized toaster that doesn't have an FMA unit?
That's a great question. The Rust standard library is really smart about this. If the CPU has the FMA instruction, and pretty much all modern CPUs do, x86 has had it since Haswell, ARM has had it forever. It compiles down to that single fast hardware instruction.
And if not?
If not, the compiler will fall back to a software implementation that is slower but mathematically equivalent.
Okay.
It does the error compensation using a different algorithm.
So we get the speed if it's available, but we get the correctness always.
Correct. You, the developer, don't have to worry about it.
I feel safer already. Okay, difference of products is in the code base. Let's move to the next headache. Equality.
The illusion of equality, as we said.
Right. Part 2. Approximate.
We touched on this in the intro. You can never, ever trust with floats.
Because 0.1 plus 0.2 is, what was it, 0.3000000000000.
Something like that, yeah. So if you write a check, if 0.1 plus 0.2 equals 0.3, the computer looks at you and says, false.
Which is just maddening.
Yeah.
So we need a function that checks if two numbers are close enough.
We call this epsilon comparison, where epsilon is your margin of error.
Let's start the function. I'm adding hashtag inline again. Not inline always this time. Just a suggestion.
Good, yeah. Let the compiler have some say.
Pub f and approximately f32 b f32 epsilon f34. So we take our two numbers and a tolerance epsilon and return true or false.
Right.
Now, I'm going to suggest a naive implementation again. Just stop me if I'm wrong. I would probably just write if fb.f's epsilon returns.
That is the absolute error check, and it works sometimes.
Okay, when does it fail?
It fails because of the way floating point numbers are distributed on the number line. It's not intuitive.
In number line.
Yeah, visualize a ruler. On a normal ruler, the tick marks are evenly spaced, right? The distance between 1 and 2 is the same as the distance between 1001 and 1002.
Right. It's linear.
Floating point numbers are not like a ruler. They are more like a logarithmic chart. Between 0 and 1, there are billions and billions of representable floating point numbers. The tick marks are incredibly close together, nanometers apart.
Okay, super dense.
Super dense. But as you go further out, to a million or a billion, the tick marks get further and further apart. By the time you get to really huge numbers, the gap between one float and the very next representable float might be larger than 1.0.
Wait, really? So you can have a number x, and the next possible number the computer can even store is like x plus 2, and there's nothing in between.
Exactly. So if you use a fixed epsilon, like a tiny number, say 0.0001.
It's way too big for the small numbers near 0, and it's impossibly small for the big numbers.
Precisely. If you are comparing atomic distances, an error of 0.00001 is massive. If you're comparing the distance between stars, an error of 0.0001 is physically meaningless because the computer's grid isn't even that fine out there.
So we need an epsilon that scales. We need a relative error.
We do. But before we write that part, we should actually keep a version of your naive check.
Why? I thought we just decided it was flawed.
Because of 0. If A and B are both 0, or very close to it, all the division involved in relative error math gets messy. You can end up dividing by 0. For numbers near 0, an absolute error check is actually more stable.
Okay, so we're building a hybrid monster. I get it.
Yeah.
Line 1 of the body. If AEB, return true.
The lucky check.
Hang on, we just spent 5 minutes saying is bad.
It's bad for correctness if you rely on it alone. But for performance, it's amazing. If you just copied a value, or if they are both explicitly set to 0.0, they will be bit for bit identical. The CPU can check that in a single cycle.
So it's a fast path out.
It's a fast path. If we get lucky, we return true and skip all the expensive math.
Okay, optimization accepted. Line 2, let diff equals AB.ABS. We calculate the absolute difference.
Yep.
Now line 3. Here's my naive check. If diff epsilon, return true.
And that's our second filter. This handles the cases near 0. If the numbers are tiny and the difference is within our absolute epsilon, we call it a match and we're done.
But if they're big numbers that fail that check, we move on to the robust part, the relative check.
Right. We need to scale epsilon based on the magnitude of the inputs.
Okay, so let abc be SAA, and let abc be equals BABs.
And we want to be conservative, so we should probably scale our epsilon by the larger of the two.
Makes sense. I'm typing let largest if abc else abc.
Abc.
A simple max function. Now the final truth test, the heart of the function.
Diff largest epsilon.
Here it is. We are comparing diff to just epsilon. We are comparing diff to epsilon percent, essentially, of the value itself.
So if largest is, say, 1,000,000, and our epsilon is a tiny 10 to the minus 5.
Then our allowed error, our tolerance, becomes 1,000,000 times that, which is 10. The tolerance grows with the numbers.
That makes so much more sense. It ensures that equality means the same thing relative to the scale of the problem you're working on.
It's a three-stage filter. First, are they bit for bit identical? No. Okay, second, are they absolutely close for small numbers? No. Okay, third, are they relatively close for big numbers? This is what you find in professional game engines and physics simulations.
This is the standard, robust way to do it. It handles that logarithmic ruler problem of floating point math perfectly.
Okay, my brain hurts a little, but in a good way. Precision and equality are handled. Now let's talk about sorting. This one hits close to home. I remember writing a high-score system for a little arcade game I was making. I had a VEC F32 of scores. I called .sort.
And the Rust compiler yelled at you.
It screamed. It gave me this long, angry error. Tradeord is not implemented for F32. And I was so offended, I was like, Rust, you were supposed to be smart. 5 is bigger than 4. Why don't you know this?
Rust knows 5 is bigger than 4. The problem isn't the numbers. The problem is NaN.
Not a number. The ghost in the machine.
NaN is the agent of chaos in the floating point world. It's what you get if you divide 0 by 0 or take the square root of -1. It's the result of an invalid operation.
And NaN has these bizarre logic-defying properties.
It breaks all the rules of comparison. If I ask you, is NaN greater than 5? Is NaN less than 5?
No.
Is NaN equal to 5?
No.
Okay, the trick question. Is NaN equal to NaN?
No. It feels like a trap, but I'm going to say no.
Correct. NaN. NaN. It is the only value in all of computing that is not equal to itself.
So if you're a sorting algorithm like quicksort or merge sort, and you're trying to put a list of things in order, and you encounter a value that is neither greater than, less than, nor equal to anything else, including itself.
You have an existential crisis. The whole logical foundation of sorting collapses. The algorithm can loop forever, it can crash, it can just produce a completely jumbled list. In a language like C++, say, trying to std.sort a vector with a NaN in it is just undefined behavior.
This means it could do anything. It could work, it could crash, it could format your hard drive.
Exactly. And Rust, being safety obsessed, says, nope, I'm not even going to let you try. It simply removes the sort method for floats to prevent you from shooting yourself in the foot.
But we need to sort things. Game leaderboards, financial data, scientific measurements.
So we build SafeCamp. The goal is to establish a total ordering. We need to be able to take any two floats, even the garbage ones, and get a definitive answer. Less, equal, or greater. No exception.
Okay, let's define it. Pub fn safe cmpa f32 bf32 sftd.cmp.ordering. The return type is that standard ordering enum.
Right.
Now, I'm guessing we need a bunch of if statements here, like if enum safe mzn is bfn dab, thus an a.enum bn game.ordering greater. Something horrible like that.
We could do that. And in fact, before Rust version 1.62, we had to. It was ugly. You had to manually implement the logic, and you had to arbitrarily decide, okay, in my program, all NaNs are considered greater than positive infinity. You had to manually handle the bit patterns for -0. It was a nightmare.
But the source code for this library is shockingly short.
It's one line.
A total CMPMB.
That's it. This function is basically a celebration of progress. In Rust 1.62, the language developers finally stabilized the total comp method.
So why do we even need our own library function if it's built into the standard library now?
2 good reasons. First, discoverability. A user who's looking for how to sort floats in Rust might not know total comp exists. But a function named SafeComp in a math library is a huge signpost.
It makes the solution easier to find.
And second, it abstracts the version dependency. If you were on an older Rust compiler, this library could implement a polyfill, that ugly manual if-else chain inside this function, but the user of the library would never know. They just call SafeComp.
I see. It provides a stable API. So what does total comp actually do under the hood? How does it sort the unsortable?
It uses a really clever bit hacking trick. It essentially tells the computer to stop thinking about these values as floating point numbers and to instead interpret their raw bits as if they were signed magnitude integers.
Whoa. Okay, that's a mouthful.
Basically, the IEEE 754 standard for floats was designed very carefully. It turns out that if you just treat the raw 32 bits of a float as if they were a 32-bit integer, they mostly sort correctly already.
No way.
Total crump just applies a couple of small tweaks to that integer representation. It flicks some bits for negative numbers to get the ordering right, and then it just does a simple, fast integer comparison.
So it bypasses the floating point logic unit on the CPU entirely.
Yes. Yeah. It creates a canonical ordering. It decides arbitrarily, but most importantly, consistently, that NaN is greater than positive infinity, and that positive 0 is greater than negative 0.
So I sort my high scores using this method, and some bug causes a NaN to appear in the list.
It will just quietly float to the top or bottom of the list, depending on your sort order. It won't crash the game, it won't panic, it will just work.
That is the safe in safe camp.
Exactly. It guarantees an answer. It turns a partial ordering, where some things can't be compared, into a total ordering, where every single value has a well-defined place in line.
Okay, we've tamed the beast, we've sorted our data. Now let's make it look good. Part 4 is smooth damp.
Right. Now we're leaving the world of abstract math and entering the world of game development and UI design.
The source description says, smoothly dampens a value towards a target using an exponential decay.
This is the code that makes a camera follow a player smoothly, or makes a menu slide into view with that nice polished whoosh effect instead of just instantly appearing.
The naive approach here is what I used to do in my old Flash animations back in the day. On every frame, I'd write something like current position plus target position, current position, 0.1.
Ah, yes. The classic multiply by a magic number method, the LERP.
It works. I mean, it kind of works. Every frame you move 10% closer to the target, it creates a nice ease-out effect.
It works if your frame rate is perfectly constant, which it never is.
What do you mean?
Imagine your game is running on an older machine at 30 frames per second. You are applying that move 10% closer logic 30 times every second.
Okay.
Now you buy a brand new high-end gaming PC, and the game runs at a buttery smooth 144 frames per second. You are now moving 10% closer 144 times every second.
The animation would be way, way faster. The camera would be super jerky.
It would be lightning fast. The entire feel of the game would change based on the user's hardware. This is a classic bug. Remember the physics glitches in older games like Quake 3 or Skyrim?
Oh yeah, when the physics would go crazy.
In Skyrim, if your FPS went over 60, plates would start flying off tables and mammoths would fall from the sky. The physics integration was directly tied to the frame rate.
We want to avoid that. We want what's called frame rate independence.
So we need smooth damp. Let's look at the signature.
Okay. Pub, FN, smooth damp, current, F32 target, F32 smoothness, F32 DTF F32.
And there's the key right there. DT delta time.
That's the time. In seconds since the last frame was rendered. That's our equalizer.
Right. And smoothness is just a constant we choose that controls how quickly the value changes. A bigger number means faster smoothing.
Okay, here's the magic math line. Let T equal 1.0 d smoothness dta.eksp.
Okay, let's break down the calculus here without actually doing calculus.
I do?
That .ext function is Euler's number, eta draw raised to a power.
The exponential function, the foundation of natural growth and decay.
Exactly. We are calculating the formula $1 e-text smoothness times text.
Why this specific formula? Where does it come from?
This is the exact mathematical formula for exponential decay. It's the same math that models how a radioactive isotope decays over time, or how a hot cup of coffee cools down, or, in our case, how the distance between our current value and our target value decays over time.
So take smoothness dt is a negative number, and a delta to a negative power is always a fraction between 0 and 1.
Correct. Now think about what happens. If dt is very small, a high frame rate, then d-smoothness dt is a number very close to 0. E to the 0 is 1, so 1.0 result is a very small number. We only move a tiny bit.
And if dt is large, like the game lagged for a moment, then d-smoothness dt is a larger negative number. E to that power is a much smaller fraction, so 1.0 result is a bigger number. We move a larger amount to compensate.
You got it. The math perfectly cancels out the frame rate. Whether you call this function 10 times a second or 1,000 times a second after one real-world second has passed, the object will be at the exact same position in its journey.
That is deeply satisfying.
It's consistent. And the exponential nature of the curve gives you that beautiful organic feel. It starts fast when it's far away, and then gracefully slows down as it approaches the target.
So the final line is just applying this calculated factor, current plus target current t.
Which is a standard linear interpolation, or LERP, but our interpolation factor is now dynamically and correctly calculated based on real time, not frame counts.
I love it. It's a utility that solves a very real visual problem with pure, elegant math.
It's the bridge between the logic engine and the user's eyeball.
Okay, we are almost done. We have these 4 powerful standalone functions. But the last part of the source isn't a function at all. It's a struct.
Part 5. the Struct F32.
A wrapper type.
This is the most rusty part of the entire library. It's where we use the type system itself to enforce correctness.
I notice a comment in the source code's edit history. FICX. Kept derived. Debug removed manual inplay to fix conflict.
That's it. Oh, I relate to that on a spiritual level. Someone probably tried to write a custom, fancy way to print the number, realized they broke something, and just gave up and went back to the automatic #derived debug.
Been there. Okay, so we're defining a new type. Pub struct F32. F32.
This is a common Rust pattern called a new type, or a tuple struct. It looks like a struct, but at runtime, after compilation, it takes up the exact same amount of memory as a normal F32. It's a zero overhead abstraction.
So it has no runtime cost. Why do it? Why not just use F32 everywhere?
Because the raw F32 type is permissive. It's a wild west of values. It allows NaN. It allows positive and negative infinity. It allows -0. It allows all these weird edge cases.
It allows dragons, and we want to slay the dragons.
We don't even want to let them in the front door. We want to gatekeep them.
Okay, let's look at how it does that. The constructor. The source says impl F32, option F32. Measure the option F32.
And that's the key. The entire secret is in the return type, option F32.
It doesn't return F32 directly. It returns an option, meaning it can either return some F32 or it can return none.
The constructor can say no.
Walk me through the logic. I call F32.new 5.0.
The code inside new, which is implied here, would check. Is 5.0 a finite number? Is it not a NaN? Yes, it's fine. Okay, return some F32 5.0.
Now I call F32.new 0.0.0.0. The result of that is a NaN.
The code inside new checks. Is this value a NaN? Yes, it is. Return none.
It refuses to even build the object.
This is the practical application of a powerful philosophy called parse, don't validate.
Explain that motto.
In many other languages, you might pass a raw float around your entire program, and every time you do some math with it, you have to wonder, is this valid? Should I check for NaN here? You end up sprinkling if Dexys is denim checks everywhere.
Or, more likely, you forget to, and the program crashes 3 functions later in some unrelated code.
Exactly. Parse, don't validate, means you perform your check once, at the boundary where the data enters your system. When you create the F32 struct from some external input, you validate it then and there. If it succeeds, you now have an F32 object in your hand.
And because the internal F32 value is private to the struct.
You cannot change it to a NaN later. There is no public method that would allow it. The only way to get an instance of F32 is through that new constructor, which acts as a guard.
So if I have a function later on that takes an argument of type F32, I don't need to check for errors inside that function.
You don't. The type itself is the proof, the guarantee that the data is valid and safe to use.
That clears up so much mental overhead. I don't have to be paranoid inside my core business logic. I could just trust the type system.
It moves all the complexity and all the validation to the edges of your program, leaving the middle clean, fast, and most importantly, correct.
It's like having a bouncer at a club. You check everyone's ID at the door. You don't have to go around asking everyone on the dance floor for their ID every 5 minutes.
That is a perfect analogy. The F32.new function is the bouncer. NaN is not on the list tonight.
Entail. Wow. Okay, we did it. That's the 5 components.
Let's scroll back at the file and look at what we've built.
Yeah, scrolling up. We have difference of products using FMA hardware instructions to defeat catastrophic cancellation.
Then a proxyq using that 3-stage filter with a scaling epsilon to handle the logarithmic nature of the number line.
We have SafeCamp using bitwise integer emulation, thanks to TotalCamp to finally sort the unsortable NaN.
Then there's SmoothDamp using calculus and exponential decay to create frame rate independent animations in physics.
And finally, Struct F32 using the type system itself as a barrier to make invalid states, like NaN, completely unrepresentable in our safe code.
It's a formidable toolkit.
Titan is a good name. It feels heavy, in a good way, like a shield.
It really shows that good programming isn't just about knowing the syntax of a language. It's about understanding the machine, understanding how the hardware actually rounds numbers, understanding what the compiler does with your code, understanding the math of the universe.
And it makes you realize just how fragile our digital world really is. A rounding error killed 28 people in 1991. A sorting error with a NaN could crash a high-frequency stock market algorithm. These aren't just academic problems.
But tools like this and, languages like Rust that encourage this kind of thinking, they give us a fighting chance to get it right.
I am definitely going to use SmoothDamp in my next little game project. And I think I'm going to start using wrapper types like F32 everywhere. The parse don't validate idea is a game changer.
Once you go type-driven, you never go back.
Well, thank you for coding with me today. This was intense. My metaphorical fingers are tired from all that typing.
It was a good workout for the brain.
And to you, the listener. We hope this little peek into the code editor was valuable. The next time you see a number on your screen, just take a second to remember the immense amount of engineering that's working to keep it there, to keep it accurate and safe.
And remember, NaN is not your friend.
See you in the next deep dive.